Good afternoon. I'm Joel Young. I lead the machine inference infrastructure team at LinkedIn. Down here is my partner, Bo Long. He leads the machine learning algorithms team. Together, we're leading a complete rethinking of how machine learning is done at LinkedIn. Today, we'll walk through what happened to start us on this journey. We'll give an overview of our products and how AI contributes, the opportunities we're facing, and how we're scaling our technology and our people to meet these opportunities. Here are some of our key products. All of these have one thing in common. You could think of them as providing a view into the economic graph. Consider your LinkedIn connections, your connections, and so on. This explicitly defines a graph, a little snapshot into the economic graph. But it's not the full graph. It's not exactly right. There's people that you work with on a day-to-day basis that you haven't connected to. And there's also people, certainly ones in this room, that if you were introduced to, if you got to meet, it's probably part of why you're here today, it would bring value to you, it would bring value to them. You can think of the people you may know product as addressing this problem, basically finding the missing edges in the graph. We have feed product, finding the information that you need right now to bring value, things like articles, new articles, updates from your connections, and even job opportunities. When you are looking for a new job, time for the next play, our job recommendations product helps you find the right job to move to. Sometimes you'll find that that job, there's a skills gap. You might be missing something. Our learning product provides recommended courses from our large library in LinkedIn Learning to help fill in the gap. By the way, there's courses in there for almost everything I'm going to talk about today, including deep learning, TensorFlow, et cetera. On our Sales Navigator platform, we help sales folks identify the influencers at companies, the decision makers, and help find a path to them to bring value. Likewise, on the Recruiter product, we help companies find exactly the right talent, people like you, to drive their mission. So it's pretty clear that all of these products have AI and machine learning at their core. How do we go about designing the AI and machine learning to address these products? Well, the key is to start at the product goals itself. Work with the product managers, work with our customers, our members, look at what are the needs, what are the budget, how much time, work and drive from that product metrics that we can measure success against. Then we work with the data science, analytics to refine the product metrics to relevance metrics, concrete measurable signals, things that will become the labels when we move on to the machine learning stage. We then join the labels with features drawn from that economic graph and move into the training stage, the modeling and training stage. We'll talk a lot more about this stage later on. Once we've trained a model, we ship it to production. When we bring it to production, we don't just throw it out there and start serving. We use an extensive A/B testing system to scientifically evaluate whether or not the new model is meeting our business goals, evaluate against product metrics, relevance metrics, performance metrics, et cetera, and make informed decisions as to whether to continue to ramp or to back off. And this is a continuous cycle. It's going continuously, constant product refinement. So, pretty clear that machine learning is driving all of this. It's also hidden places in our stack. You have things like anti-abuse, spam detection, fraudulent account detection, and also things even in the build system. You might be deploying a product and the deploy fails. Historically, when the deploy fails, it goes back to the dev who is pushing the service and they just try again. It might work this time. Why do they try again? Well, there could be one of the causes that is their mistake. The other causes could be a random hardware malfunction out there somewhere on the grid, Or it could be a bug, a non-determinism in the deployment stack. If we can apply a model to this, look at the situation when the failure happens and direct the fault to the team that's most likely to be able to fix it, we can shave off a significant amount of time and help build trust in the developers into the build system. Okay? AI is eating the software world. Many of our products have evolved over the past decade and are built from substantial amounts of carefully engineered code. In fact, we have over 100 search verticals and recommendation services providing relevance machine learning into our products. Okay? Each of these services was custom built by different teams. In the past, we've led a few efforts to try and standardize the machine learning components in the stack. Unfortunately, these have often worked. They bring value. They help bring in a new technology. But what they don't end up doing is reducing the complexity. They don't replace things. They just add another part, what I call second system syndrome. Okay. Also, we have many different modeling technologies in use. There's simple logistic regression, tree ensembles, deep learning, additive ensembles of all three of the above. Our workflows are built with things like Pig, Dolly, Hive, Spark, Scalding, Cascading, etc. Tons and tons of different technologies. Okay? Also, all of these services are mission critical to the company. Whatever we do, as we try and advance the state of the art, we need to reduce the risk of site issues. And when they do happen, we need to make them easier to troubleshoot. Okay? Also, there's some secular trends that are happening in the world. Machine learning is becoming democratized. It used to be the case that it was an ivory tower skill. You needed a master's degree, a PhD in machine learning, maybe physics. But now we're seeing people come out of boot camps, coming out of online courses, people taking the Coursera courses, people taking pretty high quality courses even in their undergrads. Okay? So at LinkedIn, what we're finding is almost every engineering team, product teams, UI teams, all of them have people with meaningful practical AI skills. Remember, again, AI is eating the software. The engineers, they want to solve their problems now. They have the skills to do it. They don't want to be blocked by the machine learning gods. But there's too much friction in the stacks. Too many stacks, too many technologies, too much manual work to gather the features, design and train the models, deploy them into production, and to keep them running. So, also, another of the secular trends is the rate of advancement in machine learning approaches, and even more in the tooling to build them is accelerating. Almost every day, if you follow the right news sources, you see big companies and labs announcing new tooling. Things like TensorFlow, Caffe2, TLC, Onyx, Spark MLlib. The list, every day the list grows longer. So we spent a fair amount of time thinking about, hey, is the right solution that we go all in on one of these stacks? Maybe TensorFlow, maybe PyTorch. But we can't know which one of them is going to win the shakeout wars that almost certainly are going to come. And most likely what's going to happen is each of these stacks are going to carve out a portion of the space. Each one are going to bring values to different classes of models, different styles of problems. And we don't want to bind in. If you look at the Clean Architecture book, the author talks about guidelines. One of the things is delay your decision making. And in any case, we already have a few texts that we know we have to build support for. So as we design, as we build our future for machine learning, it needs to be extensible by us. And not only the core infrastructure and machine learning teams, but also by our end users. Even the UI teams, they come up with a new tech that exactly solves their problem. They need to be able to bind it into what we're building rather than having to build their own thing that we're going to have to clean up the tech debt later on. Okay? All right. You've probably heard of the fundamental rule of engineering. Fast, good, cheap. Pick two. Historically, we've picked fast and cheap. Good and cheap. This brought very quick value to the particular products, but it's also part of why we always end up with a second system syndrome. We don't actually reduce complexity. This time, Bo and I are able to go in with the other two choices, fast and good. And by fast, what we're really focusing on is fast iteration speed for the modelers, fast experimentation cycle. We aren't forgetting cheap, but now it's cheap to serve, not cheap to build. So what is our particular goal? Our concrete target goal is to more than double modeler efficiency, modeler productivity. One of the things we found is that there's a direct connection between the modeler iteration speed, as long as that iteration is coupled with early feedback, directly drives improved product metrics. We're doing this focusing on the model creation stages, deployment stages, and then maintenance or running, continuous monitoring of the models running in production. Okay. We're divided the problem into a set of layers. We have experimentation and authoring, exploring the data science, exploring the economic graph, trying modeling approaches, driving down into the training layer, vast clusters, GPUs, distributed training systems, moving down into packaging up the artifacts. The artifacts can be surprisingly complicated and large, moving them into the right production environments, and then running in production. Running in production and in the training are the two places where the fast and cheap comes in. Okay. All right, threaded through all this are two pillars. We have what we call the feature marketplace. This is where we look at better technologies for generating features, things like sliding window feature aggregation, count services. Also, a feature pub sub system where you can, as a development team, modeling team, you might come up with a pretty cool feature. Maybe you have a new deep embedding that can capture a member profile, and you're getting a lot of leverage. You've heard of this idea of transfer learning. You want to share it with another team. Historically, that's been extremely complicated. What we're doing is we're separating, this is the data for the feature, this is the semantics. So features have a name. As a modeler, all you need to do is know the name of the feature. The providers of the data provide anchors in each of the execution environments. Offline, I'll get it from this Avro file, this ORC file, this Dolly view. Online, it'll come from this key value store or this REST API. Down in search, it'll come from the query, or it'll come from the inverted index or the forward index. Okay. On the other side, we have the assurance, the health assurance. Constant monitoring, constant checking to make sure that the system's staying healthy. That when we're designing a model all the way down in the authoring stage, that the features are available online, giving warning. Maybe it's okay that they're not available yet, but you want to know that part of your deployment process is going to be needing to get the features into production. Checking for offline-online consistency, et cetera. I'll talk a little bit more about this later. Okay. So how are we organizing this? Some of you may have heard of McChrystal's team of teams model. So historically, organizations are very hierarchical. You have managers reporting to those managers, you have teams. We're not doing this project in this sense. What we have instead is for each of those layers, each of those pillars, we have a lead. Usually it's an engineer, a tech lead. And the engineers working on that come from across the organization. Some of them are up in product engineering. Some of them are in our tools chain. Some of them are working in the modeling and the relevance org. Some of them are in infrastructure. Also, we have a leadership team of which Bo and I are part of. The leadership team isn't directive. We're not telling people, go do this, go do this. What we're setting is direction for the project, vision, and we're looking for places where there's friction building up, where people aren't knowing what they need to know about the different parts. Sometimes there's too much collaboration. The way things are set up, teams are having to talk too much, it's slowing down progress. Then we'll help dig in and find a better API, a better boundary between the projects. Other places, there's not enough communication. So actually, going back, since we are talking about machine learning, one of the ways you can think about this is that the leadership team, we're really just a stochastic gradient descent optimizer. We're trying to find a more global optima for the project. Hopefully not too stochastic, though. Okay. It's also distributed across the world. We have participation, active participation from our teams in Bangalore, from Europe, and from our multiple teams in the US. Okay. So what exactly do we mean when we're talking about a model? If there's one thing you can take away from this is a model, for our purposes, it's just a directed acyclic graph. It's just a DAG. You have a set of input features. You have transformations on these features. And that's it. Some of the transformations can be really simple. Things like convert a categorical feature into a one-hot. There can be linear algebra operations, interaction features, maybe do a cross product or an inner product between two vectors. It can also be very rich transformations, like use TensorFlow to compute a deep embedding. Some of these transformations in the DAG are also trainable. There's unknowns in them, wildcards that need to be figured out. So this is a notional DAG for one of our job recommendation models. We'll talk about this a lot more later on when we discuss the training. But at a high level, there's a set of input features. We have raw member profile text. We have raw job text. From the raw member text, maybe we need to compute a deep embedding, project it down into, say, a 100-dimensional real vector. Maybe we also have a set of standardized features, standardized job title, seniority, geolocations, et cetera, that have been processed, say, through streaming pipelines. From these, we might compute a deep interaction model, projection, maybe a probability of click-through using job embedding, member embedding, and we might take the output of that, all our other features, and learn a random forest with something like XGBoost. We have some other models that go into the mix we'll talk about more later, and maybe we combine them with a linear combination. Yep. So how does the engineer actually go about building a model like this? For our hardcore modelers, the way they often like to work is we just provide IntelliJ bindings for our DSLs. They work on the models just like other code, and then they use the build and deploy tooling to run the trainers and the exploration on Spark and Hadoop. For everyone else, we provide Jupyter-based exploration and authoring environment. In addition to a great interactive experience, we find that by using the Jupyter Hub, it really motivates engineers to not pull personal member information down onto their development boxes. On this slide, you can see a view into a Jupyter notebook with a notional two-dimensional title embeddings. Actual title embeddings are far higher dimensionality, but it's hard to project them. So then building the model. Now, we talked about having a DAG. The model is just a DAG. But when we represent it, what we've found is that the models get quite interesting and complex, and having a graphical drag the boxes around, it seems cool. People go, ooh, and pointy-haired bosses like me sometimes get excited about them, but they don't speed up development. They don't speed up learning. They maybe speed up the first half hour and remove the fear factor. What we need is a lot more control, a lot more insight into what's happening. And for this, we have a declarative DSL that we've built in-house called Quasar, short for quick-ass scoring and ranking. So you can, our previous one was called Loser back 4 years ago, which was short for logistic scorer, but no more negative names. So here you can see a little section of the model. We're computing a cosine angle between two of the embeddings, a member embedding and a job embedding. We're also applying a tree model to compute scores. The scores might be a probability of apply, a probability of click-through. If you can get the signal, maybe it's even a probability of what's called in the ads world a conversion, the probability that the person actually gets the job. And we can figure that out. It just takes a month or two for people to update their profiles. You know, we know that they applied, we know they clicked, and eventually we'll know if they got the job. Yep. So, also, the DSL provides what you might call as first-order operations. It can actually work on lists of entities. It can work as a ranker and not just a scorer. So you can see at the bottom, we're taking a list of all the jobs, all the documents ordered by the score. We can do top Ks, we can do filters, we can do diversities, split lists apart, bring lists together, all sorts of operations on the lists themselves. Okay. All right. So, of course, people want to be able to explore their data using the Jupyter notebooks. You get that for free. You can tie into Matplotlib, Python tools that everyone knows and, well, many people know and love. And also, we provide hooks so you can drive your larger scale work. You don't want to do heavy lifting within the notebook itself, but you know, the data is far too big to even run on a single box, even if we threw a few terabytes of RAM in. But drive it over to Spark Notebook, to Spark running on the big clusters. Okay. You can see a little notional comparison coming out of the results for two versions of the model, accuracy and area under the curve. Okay. So Bo is going to walk us through how we train the models.
Thanks, Joe. So like Joe mentioned, right, the goal of productive machine learning is to help our engineer to do model training productively. So let's take a look at how to train the model. So to train a machine learning model, we need key components, two key components. One is features, which are data we prepare for the model training. Normally, we refer each variable as a feature. Another key component is algorithm. So which take features as input, optimize the objective function, and learn a model. So feature and algorithms together, we can learn the model. Let's take a look at the feature first. So we're in the age of big data. So even for a single model, we could have millions of features. At LinkedIn, we train a lot of different models for different products. Yeah. So overall feature space is huge. As you all know, right? And in the practice, feature engineering is major efforts for the model training. One time, the professor Andrew at Stanford said, applied machine learning basically just the feature engineering. Yeah. So at LinkedIn, so to make feature engineering more productive, we built this framework called the feature marketplace. So for our engineer to share, discover, or explore the features easily. So with this feature marketplace, engineers can contribute their own feature to the feature marketplace. And through this feature marketplace, so people can easily get all the information about the features, like how a feature was generated, and which model used which features, and the history of the feature distributions. We also provide a lot of other powerful tools, right? Like how you do feature selection, how you do validation and monitoring of those features. So with feature marketplace, engineers can find the features for their model training very productively. Yeah. I also want to mention one challenge, right, specifically for the feature marketplace. So how we make sure the engineer actually gets what is asked for, right? I'm talking about the offline-online consistency. You know, when we do a lot of offline experiments to get a good feature, works very well. But there's no guarantee you actually can get the same feature online because there's always a lot of steps could be generated description between the offline and online. So we build, at LinkedIn, we build a frame or platform which gonna generate a feature offline, online based on the common libraries and the same configures. So make sure the offline, online consistency. Also, they hide the feature generation details from engineers. So the modelers only need to specify the feature name. Then they can easily get the feature for the offline training and also get the feature when they do the online model scoring. Yeah. Also, the frame also provide other powerful tools like feature joining, so make you do the feature joining very efficient. So in summary, with this feature marketplace, our engineer can easily identify good features for their model training with offline and online consistency. So after we have the feature, now let's look at the algorithm. At LinkedIn, we have three major types of the algorithm. First one is deep learning, which is a popular algorithm based on multi-layer neural networks. At LinkedIn, we use TensorFlow to train the deep learning. We use deep learning for both feature generation and prediction. For the feature generation, we generate all kinds of embeddings for the models. For example, we generate order embedding for our user profile, which can be used for the like job recommendation. We also use for the prediction deep learning, especially for some challenging tasks like language understanding and image understanding. Yeah. The second type of algorithm we use on LinkedIn is trees, basically ensemble of small trees. Yeah. So basically, we use the trees, boosting trees algorithm implemented in the open source package XGBoost. So boosting trees, it's very good at capture the nonlinear interaction within data. So we use boosting trees for both feature generation and also prediction. And the third type of algorithm, we develop our own algorithm package based on the concept of general linear mixed model, which is a powerful model for recommendation applications. As you may know, right? General linear model is a popular model for the response prediction. For example, logistical regression for binary response prediction, right? Linear regression for the numeric response prediction, and the Poisson regression for the counting response prediction. They are all the special types of the general linear model. When we use a general linear model for the recommendation, we also want to capture specific information for specific user or specific item. For example, when you do job recommendation, you also want to capture specific information for that user. Normally, we do this by incorporating the user ID features or item ID feature into the model. So you cross other features with a user ID. When we do this, we're actually doing the general linear mixer model. So intuition is very simple here. Basically, what we're doing is we have a global model which you use all the data and all the features. But on the top of the global model, you use the data only for a specific user to train a small per user model on the top of the global model. Similarly, you also train a per item model just for that item, like a job. Yeah. By doing this, you have the deeper personalization. So the idea is simple, but the computation for the algorithm is very challenging, right? Think about it. We have 500 million members at LinkedIn. Even each member model only have 1,000 features. That's a huge number. Yeah. That's why we develop our own algorithm package. Yeah. To do this general mixture model. Yeah. We also open source this actual package. Name is Photon-ML. Please feel free to give it a try. Yeah. More than that, we also generalize the general linear mixed model to the nonlinear model. So now we also support, we can choose a nonlinear model. For example, we can use the tree model for the global model. But on the top of tree, you can choose another per user model. For example, just based on logistical regression. Yeah. So it's very flexible and powerful for a recommendation. So after we have the features, have the algorithms, we also build this training engine called Photon-Connect, connect all the training process together. So this engine gonna call the frame, like I mentioned before, to prepare our features, make sure offline, online feature is consistent. Also call the different type of algorithm, do all the feature transformers based on a DAG, and finish the final model training, and we have our Quasar to do the online model serving. Of course, this is going to be a repeating process. You keep getting feedback and improve your model with another training cycle. Now let's take a look at a specific example. This example for LinkedIn job recommendation. First, take a look at the feature. We recommend the job to our members. So we have member features and job features. For job features, we have two types. One is member profile text feature, which is just a feature based on raw text information, which has a lot of information, very rich information, but it's quite noisy. Yeah. Another one is a member standardized feature, which you're gonna, based on structured data, extract the information based on standard format. It's much cleaner, but it has less information. For the job or job side, have a similar situation. Yeah. So let's look at how we generate a feature. For the raw text feature, like I mentioned, has rich information but noise. That's why we can use deep learning to extract embeddings, which remove the noise but gather more contract features. So we have the deep learning for the member and also for the job. Together, we also have interaction features, also based on neural network interaction. Now we have the feature based on the deep learning. We also have standardized features, have a feature ready. Now we do the final model training. Like I mentioned before, we use a general linear mixed model. Yeah. So first, we pick up the trees, forest, it's ensemble trees, as our global model, which will take all the data, all the feature, get a global model, can do the prediction. But on the top of the global model, we also train the per user model and the per job model. You can see per user model will only use the data for that user based on job features. On the other side, we also only use all the user feature for specific job for the per job model. And then put together will be the final model, which gonna be recommended the job to our users. After we have this model, and Joe will talk about how we're gonna deploy and how we use this model.
Thanks, Bo. So if you think about the model that Bo just talked about, if you think about it naively or brute force, what we have is over 500 million members, over 10 million jobs in our inventory. If we tried to do an all-pair solving, we'd have at least 5 gazillion member job pairs that we'd have to solve. Sorry, I can't say that number out loud. But fortunately, we don't have to do it that way. There's structure to the model. So there's the global component. This is that deep interaction model combined with the XGBoost, the tree model. We take that, those two parts, and we take the Quasar DAG, package them up, and we push them as an artifact down to all of our searcher nodes. Then, if you think about the per member components, really these are just a vector of numbers. They're the coefficients for a logistic regression. We can just take those and put them in an online key value store, indexed by, say, the member ID. We can take the per job coefficients, again, just a set of numbers, treat them as features, and just write them into the sharded forward index that's deployed to the searchers. Okay. Now, if we think about this, when a model like this is actually going to be used, we're not doing it for all the members. We're doing it for the member that is on the site. So we don't have 500 million members to deal with. We have one. So that makes the problem 500 million times easier. But even 10 million jobs is still a lot of work. How do we do it in practice? So member comes to the site. They navigate to the jobs page. And when they do that, a REST call goes down to our job recommendations mid-tier. The job of the mid-tier is to integrate everything we know about the situation. It reaches out to our standardized data stores, pulls the things like what's the member's current job, what's their industry, where are they, geolocks. It reaches out to the model store and pulls that member's coefficients. By the way, which coefficient should it pull? Well, it has already checked against the A/B test platform, which model is this particular member seeing? Okay. Then, by the way, it also uses the frame system. There may be other features. Which features did it get from the standardized one? It's the ones that the model down in the searchers are going to need. Bundles it up, sends it in the query down to the search cluster. The broker takes it apart, shards it out to a whole bunch of searchers. Then on the searcher, it takes the per member portion coming in from the query. It takes the features from the forward index, takes the global model, puts it all together, runs the Quasar inference engine. The inference engine supports lazy modes, it supports columnar modes, batching so that it can keep vector pipelines hot, et cetera. Then the results come back out. And we can do this fast enough that we give a real-time experience to our members. So we've got it running in production. How do we keep it healthy? Well, one of the things we've found, this is obvious, but it's not obvious when you're stuck in the loop. The more work you do to keep your models healthy early in the life cycle, the easier it is to keep them healthy when they're running in production. So in the health assurance thing, we add a lot of verification and validation steps. Like even down in the authoring environment, you've crafted this model. It uses a set of frame features. Are those features available online? Are they updated fast enough in the online environment to be giving you the robustness that you need? Is there checking constantly? Is there offline versions of the features consistent with the online version of the features? Trying to use the same calculations on both sides, trying to avoid some of the problems with the Lambda architecture that we see. Basically, constant monitoring, constant checking. One of the common patterns that you see, machine learned models, they're trained on a set of features. The performance of that model is going to naturally start degrading as the world drifts from the world that was in place at the time that you trained. Historically, what's detected is, we start to see business metric impacts. It must be time to retrain the model. The natural inclination is to delay that as long as possible because it's been difficult. You have to make sure the data pipelines work again. Maybe it's been a month since you've retrained. So the next step is to go look at your data and then make a guess. All right, if I retrain and deploy weekly, maybe with something like a cron job, it works good. But then the reality is that weekly, sometimes it's too slow, sometimes it's too fast. So we're either throwing away product lift or we're throwing away compute. With the monitoring system, we can be tracking this degradation, and when it reaches a threshold, we can automatically trigger retrain and deploy. So another part is continuous online anomaly detection. In a sense, not in a sense, in reality, anomaly detection is just another kind of machine learned model. So we're monitoring our model deployment system with a model trained in our model deployment system. Part of our alerting system is to actually ask the people receiving the alert, hey, was this a true anomaly? Was it an anomaly, but it's actually a new trend in the world? It's not a flaw in the system. It's just new information that we need to integrate into our modeling processes. Was it a false positive or, don't know yet, right? So talked a lot about what we're doing to scale out the technology, make it easy, but that's not enough. People are coming in more and more with machine learning skills, but not everybody. Also, we have our own stack. So people learn stuff with Weka or TensorFlow or this toolkit or that toolkit. They've got to come in and learn our own. So we've set up this thing called AI Academy. We have a blog post on it. You can read more. One of the interesting classes is we have a course for managers. So they're not going to be doing the machine learning themselves. They'll be leading people who are. And what kind of problems are actually solvable? What are they reasonably likely to get good results from? And what are still what we call AI hard problems? Also, how to evaluate success. Concepts like precision and recall and F-scores and area under the curve and how to create well-structured A/B tests and understand significance and things like that. Also in understanding, people in the audience do machine learning, you know that it's a fundamental R&D problem. It's very hard to say in 1 week we're going to have a model that's going to bring a 0.5% lift. Probably not going to happen, but it might. It could take 2 months, depending on how hard the problem is. Okay? So, who's heard of the idea of a success trap? A few people. So what a success trap is it's when a company, when a business, when a team, when an individual gets stuck in, since it's machine learning talk, in a local optima. They've learned something out of the world, they've had success, but they've overlearned, they've overfit this piece of information, and they miss opportunities. A classic one is Kodak with digital cameras, missing the transition, even though they're the ones who invented digital cameras. So there's a particular success trap that I call the support trap that I've seen happen many times with new infrastructure components. You adopt your customers. Customers come in too quickly. Each customer that joins has a finite support cost. If you bring in more customers than your team can support, the team is now frozen out. You can't continue doing strategic development. You only have 2 choices. One is you can evict customers. That's kind of a painful thing to do. Or you can try and get more resources. You can find more engineers to bring them in. But if you waited too long, now you're a bad bet, right? People have started losing face. Your customers aren't happy. You're not quite serving them. It can be hard. And even if you do get the head count, it can be slow to bring them up to speed. It's much better to avoid this. So what we're doing in the Productive ML project is we're not doing a whole-scale adoption. Instead, we're going component by component, even sub-components in the layers and pillars. In each one, teams adopt, and each adoption makes the next part of the adoption easier. So they pick something. Maybe they want to use the Quasar modeling language and the inference engine. Maybe they want to use the feature marketplace system. Maybe they want to use the monitoring stuff. We also look at each component and we rate it pre-alpha, alpha, beta, general availability, and we limit adoption depending on where it is in the curve. Pre-alpha, alpha will have very specific partners that have agreed to accept some of the risk that's involved. The benefit, of course, is when it pans out, they're way ahead of the curve on the adoption cycle. So, in conclusion, we've presented our approach to a complete overhaul on the machine learning stack at LinkedIn. You can find more at our engineering blog, and we're open to questions. You can put questions up on the Slido. I haven't seen anybody using it so far, but you're welcome to. I'll start the app up. Or you can just ask, and we'll repeat the question back. So there's still no questions. So anyone have any questions? Go ahead.
When a feature moves from a team that builds it to your marketplace, how does your platform infrastructure group support that? I mean, presumably they built it for their use case, and supporting it for a whole host of consumers might have different online requirements, offline requirements, et cetera. What is that responsibility?
Yep. That's a great question. So the question was, when one of our modeling teams comes up with a new feature, they want to publish it for sharing, how do we, in a sense, provision the infrastructure? Who's responsible for running that infrastructure? And to be honest, we're working through the details on that. Feature sharing is a lot like getting leverage with your code sharing. It's awesome, you're bringing efficiency, and you're binding yourself because now you can't change your APIs anymore. You have to deprecate and provide end of life and all that. But right now, our target is the provider of that infrastructure. I mean, the provider of the model owns their infrastructure. Now, the key value stores have SRE teams that run the key value stores. The Kafka and Samza streaming teams have SREs that run the various clusters. But just as they were responsible for the infrastructure that they used before they published it, part of their decision on the publishing is to continue the responsibility. Now, if a feature gets a lot of leverage, it's going to move to one of a couple teams. The standardization team that produces features that are generally usable for business metrics and for machine learning and relevance, or to a common features team that's more focused on relevance driving features that are generally leverageable. Thank you. There's a question over here. Yep. Yep. So the question is, for a small team of the modelers, it can be a big challenge to move from that to getting a full-scale model in production. Did I get that about right? Okay. So this is a big part of what we're trying to do, and this is where the democratization comes in. By using the components in our architecture, starting with the Jupyter notebook tied in with the Quasar DSL support, the frame support, tying over to the Photon-Connect that Bo talked about, basically a team, if they use this infrastructure, they're greatly increasing the probability that what they build will be deployable using the rest of the infrastructure. We're not going to block anybody. If somebody wants to go out, try something new, do their own thing, they can, but they're going to be on their own. They're not going to get support from the relevant site reliability engineers, et cetera. Any other questions?
Yeah. Are you guys doing like collaborative with the massive install? Do you guys just want to be really, really big in that space, or do you figure out any ways to improve the
So the question is, what are we doing with hyperparameter tuning? Yep. Do you want to talk about?
Hello? Hello?
Can you turn on the mic?
So that's a very good question, right? Actually, I should mention that. So like we said, we have a so huge feature space. That basically means that we have the huge parameter space. So we actually built a component called auto tuning. So we can automatically tune the parameters, even for the complicated model, like you put the nonlinear model tree and the linear deep learning together, which is based on the Gaussian process. So that helps hyperparameter tuning a lot. Yeah. Yeah. Yeah.
Any other questions? Yep.
Do you experience any issue like having managers being a part of the product of the solution, machine learning related?
So the question is, we have the course for the managers. Have we had any issues with the managers? Say it again.
Being a part of the problem instead of the solution.
The managers being part of the problem instead of the solution. So truth in advertising right now, the machine learning infrastructure that we have is more, at this point in our productive ML, pro ML evolution, it's more like the old way where it's awkward and difficult. Right now in our classes, there's every person who goes through the machine learning process, the AI Academy, is partnered with somebody in the relevance team for an apprenticeship. So we're only taking product eng teams that have partner relevance team, machine learning teams, and they're working through together. So there's a fair chance that we will see issues like you're talking about. And one of the things, it's actually pretty likely because engineering managers at LinkedIn are engineers. They actually build things. And that means that some of the managers might take both classes. They might take the how to do it and how to manage it classes. Hopefully with the two, they'll avoid being part of the problem. But we welcome stress, right? It's only by people trying things that were on the edge of our envelope that we learn in advance. So there's going to be challenges, and they're going to be good ones, I think. Okay. Other questions? Going once, going twice, session's closed. Thank you.